Okay, so let's look at the motion of satellites as a good example of circular motion. Okay, so let's see if you remember. I hope you remember. What's the equation for centripetal force? What is it? Mika, what is it? Fc equals what? Right? Okay. And remember, that's the force that moves something in a circle. It's the force that points towards what? The center. So in our example that I just showed you of the orbiting bodies, the only force would be what? What would be the only force? What's the only force that acts on the Earth? Gravity, right? Now, did you study the universal law of gravitation, grade 11? Do you remember what the equation is? Yeah, it's this one. It's Fg equals big G m over r squared, right? Where this is mass 1 and this is mass 2. You remember that? Now, if you look, this is an equation for force. This is an equation for force. And because we know that all equations for force are, we can basically substitute one into the other. We can actually substitute this equation into this one. So we can set them equal to each other. We can say, in a system where we have like the Earth going around the sun, the centripetal force is the force of gravity. So we can set them equal to each other, and then we get this. So one of these has to be the Earth, and then one has to be the sun. Okay? So if one of these, so if we talk about the sun and then the Earth going around the sun, this little m on this side would refer to what? It's the object that's moving. It would be the Earth, right? So one of these would be the Earth, and you'll notice that in this, the Earth's mass is irrelevant. The Earth is a satellite, okay? So the word satellite means anything that's orbiting a much bigger object. So whether we're talking about an actual satellite, like the one that gives you television feed, or the one you use for cell phone transmission, that's a satellite. The Earth is also a satellite. What would be the Earth's natural satellite? The moon, right? But the actual mass of the satellite is actually irrelevant, because you can see that they actually cancel out. So you're left with this. You're left with this equation. V squared, now if we get rid of it, if we move the r, V squared would be big G mass of, I'm going to put mass of the planet, but even that, really, I shouldn't write mass of the planet, because if this was the Earth and the sun, this would not be little p. What would it be? It would be actually the mass of the sun, right? So this is the sun or the Earth. Most likely in questions that you're going to get, it's either going to be probably the sun or the Earth, okay? Over r. So there's your equation for the speed of any satellite traveling around an object. And then we can actually simplify it further and get rid of that v squared. Oops. We'll get rid of everything. Okay, so there it is. So V is equal to the square root of big G M over R. Now, you remember what big G is? Remember what big G is? It's a gravitational constant. So if it's a constant, that means that's a very specific number. And it's 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay? All right. So, in this question, we have a satellite. It's orbiting 1,000 kilometers above the surface of the Earth. So what would be the speed of that satellite? If the only force acting on it is the force of gravity, what would be the speed of that satellite? So that would be V equals square root of big G. Change the color. So 6.67 times 10 to the negative 11 times, this is the, would be the mass of the Earth, which is about, I'm going to round it off. It's about 6 times 10 to the, I believe it's 24 kilograms over, who's that now? Since I can't draw a straight line, we'll do this. Okay, over the radius. Now, the radius is, okay, R. Now, this is, be careful with questions like this. This is 1,000 kilometers above the surface of the Earth, okay? So imagine that this is the surface of the Earth. The satellite would be here. This distance from here to here is 1,000. But the radius is always with respect to the center of the body that you're orbiting. So that would be somewhere over here. So we need to figure out what this entire distance is. So it would be the radius of the Earth plus that 1,000 kilometers above the surface of the Earth. So what's the radius of the Earth? Someone look it up. What is it? What's the radius of the Earth? I believe it's about 6,400 kilometers, but I could be wrong. Jara, what is it? What is it? What is it? Sorry? Okay, I'm just going to say 6,400 kilometers. So I'm going to say the radius of the Earth is 6,400 kilometers. Now, we have another 1,000 kilometers from the surface of the Earth. So that total radius would be then 7,400 kilometers. Okay? That's the total radius of this orbit. We're assuming it's a perfect circle. Okay? Now, I'm going to make a mistake. You see if you can figure out what the mistake is, alright? So our equation is square root of gm over r. Okay, what's the problem? What do we need to do before we proceed? Now, I didn't put the units in. I'm lazy. But if you look at the unit for big G, it tells us that the distance has to be in what? Meters. And this is in what? Kilometers. So we need to tack on 3 more zeros. 1, 2, 3. Or we can rewrite this as 7.4 times 10 to the 6. So 7.4 times 10 to the 6. Okay, so what is that? So just by looking at it, 6 times 6.67 is about 40, no, it's about 30, about 40. So that's about 40 times 10 to the 13 over 7 times 10 to the 6. It's probably close to about 6 times 10 to the 7. So your answer should be, I'm assuming like 8 times 10 to the 3, somewhere around there. What did you guys get? Just ignore my chicken scratch and just try and do this mentally in my head. Huh? I said about 8 times 10 to the 3. 8,000 meters per second. 7353? 735. I remember I just did it in my head, right? Okay. So 7353 meters per second. Okay. So I said about 8,000, so we're in the right ballpark. I'm assuming this is right. Okay? Okay. Alright, so that's the speed of the satellite. Now I'm going to ask you a different question. And it's very similar, okay? But it's going to be a little bit different. So I'm going to show you that one now. We're going to talk about a geosynchronous orbit. All right? Oh, sorry? Still copying this? Shall I pause? You're done. Okay. Okay. So here's a follow-up question. And not much information. By the way, remember the mass of the satellite is what? Irrelevant, so we don't need the mass of the satellite. Now, this question asks about a geosynchronous orbit. Do you guys know what that means? No? Okay. So a so if you picture, this is the Earth. This really awful thing is the Earth. And this is the satellite. Imagine we pick a point on the Earth. So imagine this is my point. And here's my satellite over here. Now, as the Earth rotates, if my point is here now, that satellite is in the exact same position relative to that point. Okay? So in a geosynchronous orbit, the satellite's always in the same spot because it's rotating with the Earth. Okay? Now, that's what's meant by geosynchronous orbit. So that tells us something. It tells us how long it takes for the satellite to rotate once around. It would have to be what? Same as what? Same as the Earth. Right? How long does it take the Earth to rotate once? 24 hours. So that satellite's going to have to rotate the same rate, 24 hours. Okay. So how far does the satellite need to be in a geosynchronous orbit? I'm going to go back to my equation for the one we just looked at, which was this one. Okay. Now I'm going to go back to this equation. Remember we set up Fc equals Fg. So I'm going to go back to that equation, and this is what it looked like before we put in the square root, right? So the mass of the planet over the R. So before I put in the square root of it, this is what the equation looked like. Do you remember this? Okay. Yeah, because we're talking about over the Earth, right? So it's the gravitational constant times the mass of the planet over R. Once again, this is from the work we just did before. Okay? So this is our equation. Now I'm going to ask you another question. If we envision this as a circle, right? Tell me if this makes sense to you. The speed is also the distance over the time, right? Does that make sense? Okay. The distance of a circle would be what? Circumference, which is 2 pi r. Okay? The time around for one cycle, if you remember your waves, is what? What's that known as? To complete one cycle. What's that? Period. Very good. And that's given the symbol big T. Remember this from years ago? What we can do now is we could actually substitute this into V. And we can say, okay, V squared. Well, we can say, okay, if you square this, you get 4 pi squared r squared over the period squared is equal to big G mass of planet over r. Nika, you okay? Giving me a funny face. You sure you're okay? Now, the reason why I'm putting in the period is because, well, if you think about a geosynchronous orbit, we have information about how long it takes to go around the Earth. It's the period of the Earth. Okay? We don't have to do it this way. We can just figure out, no, you have to do this. You have to do it this way. I'm sorry. Just scratch my head. You have to do it this way. Because you don't know what that radius is. If you knew what the radius is, you wouldn't have to know that. Okay. So what I'm going to do is I'm going to isolate for r. I'm going to get rid of this r. And I'm going to move it to this side. So that's going to give me r cubed on this side. Okay? And then I'm going to get rid of the period. It's going to be G, big G, mass of planet, period squared, over 4 pi squared. Okay? So all I did was just got rid of everything on this side and moved it here. And I got rid of the period. I moved it into the numerator. So there's my equation for radius. Okay? So let's work it out. Okay. So what's big G? 6.67 times 10 to the negative 11. The planet, I'm going to round it off to 6 times 10 to the 24. Now, the period. All right. The period is got to be in what unit of time? What's the unit of time for the period? No, it's not minutes. It's remember, frequency cycles per second, so it's got to be in seconds. So one period for the rotation of the Earth would be 24 hours times how many seconds per hour? 60 minutes times 60 seconds, so it'll be times 3,600. So what would that be for the period? What is it? 86,400 seconds. So we can put that in here. 86,400 squared. Because I can't draw a line. I'm terrible at that. I'll just do this. There you go. I'll go back to my trusty pen. Okay. Over 4 times 3.14 squared. Okay. So what is that? What's that going to give us? So work that out. So that's 7.5. Well, just by estimating, this is close to 10 to the 5. It's very close to 100,000. So 100,000. No, that's not really close to 100,000, but 100,000 square will be about 10 to the 24. Hold on, wait. You're taking the cube root, not the square root.
Okay, so 9.1
Like, give me the number before you cube it. Yeah. What's the number before you cube root it?
7.5 times 10 to the 32.
Yeah, that sounds right. You divided it by this? Times 10 to the... Okay, so now take the cube root. 9.1. You guys get that? Wait, let's pause it. Okay, so it's 7.5 times 10 to the 22? Yeah, that's on video. No swearing, please. Okay, so let's work at the cube root of that. So what's the cube root of that? 4.2 times 10 to the 7. Okay, now, let's see if it makes sense. What was the radius of the Earth? What was this distance? We said it was 6,400 kilometers. 6,400 kilometers. But 6,400 kilometers is the same as 6.4 times 10 to the 6 meters. So this satellite, which is over here, this is the radius of the entire orbit. So the actual height above the surface of the Earth would actually have to be the difference between this value and the radius of the Earth. So what would that be? Should be like 3.6 times 10 to the 7? No, 3.6 times 10 to the 6, right? 3.5 times 10 to the 7? Yes. Okay. And these numbers are all double checked? Okay. Seems pretty far. Yeah? But it's got to be meters. Yeah, it's got to be meters. So it's got... Okay. Guess it's okay then. Alright, so let's stop there. Okay. I'm going to trust you guys that the calculations are right. This is my bottom line when I put the video up. Okay. Now, what you guys are going to do, you guys are going to get started on this, okay? So what I have for you guys, you're going to get started on, the assignment's not actually complete. So you can continue working on it tomorrow. I'm going to give you time tomorrow. So this is the assignment, right? You're gonna do, your job right now is to do 4 things, and then the 5th one I'm going to finish writing it off. Okay. So you're going to be looking at just the first part is look at the orbit itself. And then we're going to do in 2 and 3 and 4, we're going to change something in the orbit. So for example, for 2, we're going to look at the period, which is how long it takes to go around. And we're going to look at how the distance affects that. So I'll give you an example. So if we go to, we're going to do this. This is the one we're going to use, sun and planet. Okay. Right now I have, this is the mass of my sun relative to the body of the Earth, which would be the Earth, sorry. This is where the Earth is located. So it's 150 units away, whatever that unit is. This is the speed of the Earth. I can reverse that by making a negative. It doesn't matter, okay? So right now I can figure out how long it takes to go around once. There's my timer here. And I can look at how long it takes to go around one orbit. But that's at this distance. I can change that distance. And figure out how long it will take to go around. Okay? That's one of the tasks. And one of the tasks you have to one of the tasks you're going to change the distance. Okay? Now 350 was not one of your options. You're going to go 75, 150. You're going to go from a small distance to 200. And then you're going to graph that data and see how the orbital period is affected by how close you are to the sun. Okay? In the third one, we're going to do something similar. We're going to reset, but this time we're going to change the mass of the sun. So we're going to go back, reset everything. So just go back, select sun and planet, reset, but this time we're going to change the mass of the sun and see how that affects the orbit. You'll notice that it changed. If I make the mass bigger, if I make the mass smaller, changes it, right? The fourth is a binary system. So we're going to set up a binary system. The binary system is when you have two stars orbiting each other. This is actually pretty spectacular. Now our sun is not like that, right? Our sun does not orbit another sun. So, but there are, I think it's like 50% of the stars out there are, I'm not sure. I believe it's quite a high number are actually binary. So for a binary system, what you're going to do is you're going to change the mass of the other one so that it's the same mass as the other sun. Okay? So they're both the same mass. And what you're going to do is you're going to change the velocity. So I'm not going to make the sun stationary. You're actually going to give it a speed. Otherwise, you're going to get a nice pattern. I didn't even give it a speed. Or did I give it a small speed? We're going to give it the same speed, but opposite direction. Okay. Now, we're going to start with a smaller distance. Like 40. And we're going to see what happens. And then what we're going to do is we're going to increase that distance. Make it bigger. Let's say like 500. Yeah. Well, what happened? Where did the other one go? Where did it go? Too big. Okay. Now, your job will be to study the effects of the different masses. So you're gonna set up a system, and you're going to change the value of the mass. So here are your initial values. You're going to change the mass to 100 each. The distance will be 50. The velocity will be plus 120, minus 120. And then you're going to run the simulation. Then you're going to compare what happens if you change the mass of each startup from 50 to 250 to 450 to 650 to 850. And then you're going to explain what's going on. And then I want you to actually compare it to a real-world example of two binary systems. Okay? So you're going to do some research. Two examples of stars that are orbiting around each other and how fast they're orbiting. Some of the numbers are staggering. And then I'll explain this last part tomorrow. Okay? All right? So you guys can get started. Okay. I will be right back.